Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X published on August 11, 2025, about 5 days ago. The headline result is a full sim-to-real pipeline that learns from large human motion data, tracks highly dynamic skills on real humanoids, and then uses guided diffusion to control those skills for new tasks without retraining. The paper is titled BeyondMimic, From Motion Tracking to Versatile Humanoid Control via Guided Diffusion. And as we will see later, the implications for general humanoid control are substantial. In short, the system handles cartwheels and spins, then achieves zero-shot waypoint navigation, joystick teleoperation, and obstacle avoidance. Building on that, the tweets highlight open source code, a motion tracking to guided diffusion pipeline, and real demos, like cartwheels and obstacle avoidance, with one post linking the preprint. Engagement looks strong. Alright, this overview graphic shows the full pipeline end-to-end. At the top, 3 panels depict training motion tracking policies for different skills, which then feed into a single state and action diffusion model via offline distillation. Below the dashed line, guidance signals steer the learned behaviors. The left panel illustrates waypoint navigation with an obstacle, while the right panel shows joystick-style velocity commands for yaw and forward motion. Together, these pieces demonstrate tracking, distillation, and zero-shot control. Next, this table catalogs the motion segments evaluated in simulation and on real hardware, giving a quick sense of coverage and duration. The left column lists names like walk, dance, run, and jumps across multiple subjects. The middle column shows simulation coverage marked as full. The right column reports real-world time ranges in seconds, indicating which slices were executed on the robot, for instance, walk and fall, and get-up segments with multiple contiguous intervals. Continuing with the results, this table reports success rates when the diffusion policy uses different state representations. The top row shows body position state, which means Cartesian body points, achieving 100% in walk with perturbations and 80% in joystick control. The second row shows joint rotation state, which drops to 72% for walk with perturbations and 0% for joystick. The clear takeaway is that Cartesian body positions transfer more robustly for control. Now, this ablation table quantifies how adaptive sampling speeds things up and rescues hard skills. The left column lists motions, while the 2 right columns compare training iterations without adaptive sampling versus with adaptive sampling. Notice the big cuts: 3,000 to 1,500 and 2,800 to 1,800. More striking, several sequences that previously failed, like cartwheel and jump spinning, converge with 8,000 to 10,000 iterations once adaptive sampling prioritizes the troublesome segments. Wrapping up, 2 takeaways stand out. First, a single motion tracking recipe scales from stylish walking to cartwheels on real hardware, thanks to adaptive sampling that targets failure cases. Second, guided diffusion turns those skills into zero-shot control via task cost guidance, enabling navigation and teleoperation. Guided diffusion means sampling trajectories while nudging them with a task cost. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.